Welcome to a video lecture. In this one, we'll look at the wave-particle duality, and this follows along in chapter 29. This is the first section of your textbook. So here we go. An interesting, slightly childish video, but I like this one.
Here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right, so I know that's kind of a little childish and maybe a little bit corny at the end. It's kind of crazy, though, when you actually start thinking about it. Electrons themselves and photons, which are particles of light. Photon is it's a particle that has no mass, but it is. We say that it still has a particle. It has no rest mass. Let's put it that way. And it is something that exhibits wave qualities. It's a light wave, is what it is. And similarly, electrons, particles, they are a particle. They have mass. We have an ability to measure the mass of an electron. We can tell that the electron also has wave qualities. Now, when you go and observe which slit the electron goes through, you are causing, by doing that, you're sending a photon, you're hitting the or something to detect what the electron is doing. And by doing that, you are changing the interaction that happens. And so, and as it mentioned there, you're taking away the wave properties. Not fully true, but it's more along the lines that you are interfering with the electron before it hits the screen. So that way it does not interfere afterwards. And this kind of gets into some of the really crazy stuff in quantum, some of that cool things in there. But so when you observe the opening or observe what part it goes through, you are taking away the wave aspect by observing it. And this is just because you are causing it to interfere with itself before it hits the slit.
In 1905, Albert Einstein published a series of papers that many consider a starting point for the modern age of physics. But other than E equals mc squared, most people only know that Einstein was famous, not for what he was famous. Since this week marks the 133rd anniversary of his birth, as is customary in Western traditions, we will celebrate by taking a brief tour of his scientific publications. Today, his paper from March 1905 on why light is a particle. Einstein didn't just pull this idea out of thin air. He first noted that the light emitted from something hot, like a light bulb filament, actually has the same energy distribution as a gas, which is somewhat surprising if you're a 19th century physicist who thinks that light is a continuous wave, and very much not a gas composed of individual molecules. And while the idea that light behaved kind of like a gas was already well known before Einstein, no one had taken the logical but crazy next step to conclude that light must then be made of individual particles too. So Einstein proposed that these light quanta were in fact real particles that could account for a few recent and unexplained experiments having to do with knocking electrons off of metals and gas molecules. He turned out to be right on all counts and got a Nobel Prize for his work. But that's a story for another day.
So as I've already started to say, a photon is a massless particle. It has no rest mass because we assume that it is always moving at the speed of light. But it is a particle because it has the ability to cause a change in other things, or have a collision with other objects that we know have mass. And it does exhibit wave qualities we've seen through the double slit experiment of Young. So it's more of this wave and particle duality. The photon is really just the quantum nature of light. And from that, I mean, it's really what all electromagnetic radiation is. We say it's a photon or whatever. It just depends on the energy of that photon. So this is getting into quantum mechanics, and it starts to get pretty crazy as we move forward. So let's keep going, and yeah, have a good night. I'll see you tomorrow in class. Have a good one.